As we mentioned before, everything in nature is made of electric charges. Our own bodies, when we look at it fundamentally, are made of these protons and electrons. In most everyday matter, the positive and the negative charges are equal, and hence they cancel each other out, producing a zero net charge. However, there exist certain substances where the negative charges or the electrons of the atoms can move freely. These substances are called conductors, as they act as very good mediums for the flow of charge, or equivalently, the flow of current. Below are examples of some conductors. Conductors have a large amount of such freely moving electrons, and hence act as very good mediums for the flow of electricity. There exist materials though which have a small number of freely moving charged particles. These materials are called semiconductors and allow only a limited amount of charge to flow through them. Insulators are substances that have no free moving electrons, hence they are incapable of generating any flow of current. So how do these free electrons behave inside a conductor? In the absence of any external force, these free electrons travel in haphazard directions due to the thermal energy of the conductor. There is no net movement of electrons in any direction, and hence no electric current is formed. Now, when we apply an electric field by placing a positive source charge on one end and a negative source charge on the other end of the conductor, an electric potential difference is set up. Let's take an analogy using the gravitational field. What would happen when you skydive from an airplane? As you dive down, your body automatically accelerates. The fall causes a loss in potential energy, which is automatically converted into acceleration or kinetic energy. There is no force or effort required from your end as you're moving in a direction of the gravitational field. But what would happen when you walk up the stairs? In this case, you will have to exert force to move against the direction of the gravitational field. This exertion of work adds potential energy to the object. Let's see how this applies to the movement of charges under an electric field. Electric field direction for a positive source charge is always directed away from the positive source, while the field direction for a negative source charge is directed inwards towards the negative source. Remember the law? Opposite charges attract and like charges repel. So if I have a negative source of energy and a positive charge right here, there will be no work required for the positive charge to move towards the negative source of energy as opposite charges attract. But what would happen if I have to move this positive charge from this point, let's call it A, to point B? That would be going against the electric field caused by this negative source and will require us to push this way. To reach point B, we have exerted a force through a distance. Remember, work is nothing but force times distance, and work is energy. So what happened to all this energy we gave this positive charge? It couldn't just disappear, could it? The law of conservation of energy says energy can neither be created nor destroyed. It transforms from one form to another. That energy we expended is transformed into potential energy. So the potential energy of the positive charge at point B is higher than at point A. This is called the electric potential, which is the work done to move a charge from a lower potential to a higher potential. When we have an electric field applied on a conductor, a force is exerted on the free electrons which cause them to move in one net direction. So, does the haphazard movement of the electrons disappear under an electric field? Not really. These electrons still travel in haphazard movements, but at the same time, they all drift in one direction. It is this drift which is the electric current. The average speed at which these electron particles drift is called the drift velocity.